Hello, welcome to internal resistance part 2. So we're going to look at the equation now, the circuit equation. So I've drawn a little circuit here. It's a series circuit, so you should instantly know a few things about it. I've got a cell here with EMF here and internal resistance little r. And I've got that in series with a resistor of resistance capital R. And as usual, the wires are considered to have zero resistance. And because it's a series circuit, we've got a current in it, capital I, and it's going to be the same everywhere in the circuit. And that's important. The current through this resistor, big R here, is going to be the same as the current through this little resistor here, little r. Another thing that I can add to this circuit is imagine that I now place a voltmeter in the circuit. Now, you could never put a voltmeter across this little resistor here because it would always have to be across the EMF and that. So that's why we have a slight problem with internal resistance questions. So what I can do is place a voltmeter either across the resistor or across the entire cell. And if you think about it, that's the same thing. So I'm going to place it across the middle here. And that's reading, and you can think of it two ways. You could say that it's reading the terminal potential difference of the cell, or it's reading the potential difference across this resistor, because they're the same thing. Now, all we're going to do now is really apply Kirchhoff's second law, which says that the sum of the EMFs equals the sum of the potential differences, and also apply V equals IR. And in fact, these really aren't hard. You can just consider all of these problems as if that really is a resistor, and then everything becomes quite straightforward. But I'll show you where this circuit equation comes from. So if we start, we'll start by stating Kirchhoff's second law, which is the EMF, that's this here, and that's the energy gained by the charges, is going to equal the potential difference across this resistor here, so that's, let's call that capital V, plus, well, some work is done getting through this internal resistance here, so I'm going to say that little v worth of volts is used up there, plus V. Now, you don't normally see this written down as part of the derivation, but I think it helped me anyway. Now, let's rewrite that. We can say that the EMF equals this V, it still does, and then we've got this current flowing through the circuit. So this little v here is going to equal the current through this cell multiplied by its resistance. So big I, because it's the same everywhere, times the internal resistance of the circuit. But then you can probably spot that if we've done this here, could have done the same thing here. This big V is going to equal the current in the circuit, the same value again, multiplied by that resistance. So we get the EMF equals IR plus IR. And really, that's just showing that this is the sum of the potential differences. You could then just change this, and this is the way you would normally see it. I think this is the way it is on your equation sheet, that the EMF equals I, oh, where's my brackets, plus R. And that's the circuit equation. And basically everything to do with EMF involves you using some form of all of these. They're all basically saying the same thing. Now, one of the things that you might want to do is measure the EMF of something. And I think before we do that, it's worth realising that all of a sudden this internal resistance is going to be important, and it's going to affect sort of how many volts go missing here, how many lost volts there are. let me just show you. So let's call this the effect of internal resistance, which I can't write. Okay, so I think the best way of thinking about this is just think how the size of the current is going to affect the number of volts that are lost, or the number of lost volts. I've just realised I'm saying lost volts without telling you that this is actually a term. I'm going to go back here. These volts here are called lost volts. They're the ones that go missing. Okay. So let's have a look at the effect of the internal resistance. So I'm going to start off with, let's have a cell of internal resistance 2 ohms and a EMF of 4 volts. I put that in a circuit, do my dotted line all the way around the edge, not very good at that. And let's imagine in this circuit, the external circuit is such that 1 amp is flowing through this circuit. So let's work out the number of lost volts. So the lost volts, and that means the little V here, well, V equals the current in the circuit times the resistance, which is going to equal 1 times 2, equals 2 volts. So in this circuit, with 1 amp flowing and a 2 ohm internal resistance, the number of lost volts is 2 volts. So if you put a voltmeter across this cell, it wouldn't read 4 volts, it would read 2 volts. 2 volts lost. Now if we change the external circuit, and I'll redraw it, so I'll draw it quickly as I can, sorry if it's a bit scrappy, same internal resistance of 2 ohms, same EMF of 4 volts, same dotted line round it, but this time let's imagine we had 0.5 amps flowing through this cell. What's going to happen then? Well, you probably can see lost volts, V equals IR, that's going to be 0.5 times 2, 1 volt. So the number of volts that are lost due to the internal resistance really does depend on the current in that circuit. It depends on the type of circuit that cell is used in, and this becomes important later on. So we can also use sort of another idea now to sort of think to ourselves, well, could we use this to figure out what the EMF of the cell actually is? And the answer is yes. And this is one of the ways, and there are 2 ways that you'll have to know for finding an EMF. So finding EMF. And the simplest way is not perfect, because what you would do is you'd get your cell with internal resistance, and you would connect it to a voltmeter. Now this only works if it is an ideal voltmeter. Hopefully you know what that means. It means that the voltmeter has infinite resistance, and if it's got infinite resistance, the current is going to equal 0. And if the current's equal to 0, no work will be done going through this internal resistance. And if no work's done going through that internal resistance, no volts are going to be lost. So in this case, with no current flowing, the terminal potential difference, which is what the voltmeter measures, will be the same as the EMF of the cell. I'll write that down. The terminal potential difference equals the EMF. That's in words. Some of you might prefer an equation. So if we go back to our circuit equation, I can show you this way. If we write this version of the equation down, where the EMF, which I've done really big for some reason there, is V plus IR, in the circuit that we've got here, with the massive resistance of this voltmeter, the current is equal to 0. So this term in the equation becomes 0. So we get the EMF equals the terminal potential difference. So you can just measure it and you're done. Okay, so there are a couple more things to talk about with EMF. A couple of weird bits, and I'll get another piece of paper for that. Here we go. And we've nearly finished. So I'm going to call this weird stuff. And it's the sort of things that exam questions are about. And I guess the first thing is to think about what happens in a short circuit. It's not ever really something you talk about in lower school, short circuits, but imagine this circuit here. And this is key stage 4 or key stage 3. So not what we've been talking about now, just what we've imagined so far. So I'll have a 1.5 volt cell. And remember, in key stage 4, there was no such thing as internal resistance. We'd never met that idea before. So I'm going to just connect a wire of 0 resistance, or negligible resistance, to that cell. Now, common sense is that, well, we've got a potential difference pushing the current round, no resistance to it. The current should get really big. Let's see how big the current should get if we were still in key stage 4. So current is equal to V over R. Well, our V is 1.5 volts divided by our resistance, 0 ohms. Doesn't work. Really, we'd be saying that what would happen is, as this got smaller and smaller and smaller, the current would approach an infinite current. And you can't divide by 0. So this is just completely wrong. So this is what really happens. So let's call ourselves key stage 5. So we've now introduced the idea that we've got a cell, and I'm going to still say that this has an EMF of 1.5 volts, but it has internal resistance. Let's go with 0.5 ohms internal resistance. And I will still short it. So the wire here, 0 resistance effectively. Don't forget my dotted line. Now, short circuit, we do still get a large current, but it doesn't keep on getting bigger because of this internal resistance. So we're going to write the same equation as this, but we're going to use the new symbols that we've met. So I'll go back first of all to the circuit equation. EMF equals the current times the external resistance of the circuit plus the internal resistance of the circuit. But I've just said that R equals 0. So I can cross that out. So we get our EMF equals I times little r. So the current is going to equal EMF over R equals 1.5 over 0.5 equals 3 amps. And that's the most that this cell would ever be able to deliver. If we made this internal resistance lower, the current that you would get would be bigger. And this is used sometimes. Things like car batteries need to provide a massive, massive current in order to get the engine to turn. I think it's about 100 amps. So car batteries have a very, very low internal resistance. But there's another symptom of that, that as the car battery delivers that 100 amps, there'll be a lot of lost volts and the terminal potential difference drops. And that's why sometimes, especially on older cars, you see that the lights dim as the engine gets turned on. And then finally, in fact, I'll go to a new side of the paper, how you would measure this experimentally. Measure experimentally. And really this is quite straightforward, but it is probably the most common of all exam questions. So explaining how you could do an experiment to determine the EMF and the internal resistance actually of a cell. And it works like this. You start off with a cell like this with internal resistance, but both of those things are unknown at the moment. You're going to place in a circuit a variable resistor, and you're going to put a voltmeter in the circuit to measure the potential difference across the variable resistor, which is the same thing as measuring the terminal potential difference of the cell. And then you're going to realise that I've missed something. We're going to put an ammeter in the circuit as well to measure the current. Now, this experiment is unusual. We do not really care about the resistance of this. This is just to give us a range of different values of the current and the terminal potential difference. And we're going to use this equation. EMF equals V plus IR. So if we rearrange that, we get the terminal potential difference is the EMF minus the current in the circuit multiplied by the terminal resistance. Now if you compare that with y equals mx plus c, y equals, well, sorry, I've drawn it the wrong way round, but look, mx, I can't write the letter c now, c, it's the equation of a straight line, which means that the intercept, if we plot a graph of potential difference against current, the intercept will be the EMF, and the gradient, that's Rm, our gradient will be minus R. I really could have written that a little bit better. I'm going to write it again over here, just exactly the same equation. So V equals minus RI, that's that bit, plus the EMF. That does look a little bit more like y equals mx plus c. That might help you, that might not help you at all, sorry. And then if you plot this graph, this is the last little bit, plot a graph of V, terminal potential difference against the current in the circuit, you should get a straight line with a negative gradient. The intercept is going to be your EMF, and the gradient is going to be equal to minus the internal resistance. And that's all.